Imagine yourself by the shore at night. The air is warm, the waves gentle. The sea is dark, almost black, stretching to the horizon beneath a quiet sky filled with stars. You listen to the soft rhythm of the tide, each wave folding into the next, like a slow breath. And then, something extraordinary. The water stirs, and a shimmer of blue light curls across the surface. Each ripple glows, as though the stars above have slipped into the sea below. When you trail your hand in the water, it sparkles, leaving glowing threads behind your fingers. Every step in the sand sends a faint halo swirling around your feet. The ocean has come alive with its own kind of fire, soft, ghostly, yet full of wonder. This is bioluminescence, a secret language of the sea written in light. It is both ancient and fleeting, a reminder that the ocean holds mysteries we can feel but never fully grasp. Tonight, we're going to drift into that mystery. We'll explore why some seas glow, the creatures behind the light, the chemistry that fuels it, and the places on Earth where this magic gathers in greatest brilliance. So let yourself sink into calm, breathe slowly, and follow the light. When we think of light, most of us imagine fire, lamps, or the warm glow of electricity. All of these lights share something in common. Heat. Fire consumes fuel. Light bulbs glow hot to the touch. Even the tiny LED on your phone carries a little warmth. Yet in the sea, countless living beings have learned to produce light without fire, without filaments, without heat at all. This is bioluminescence, literally living light. Bioluminescence is sometimes called cold light. In technical terms, less than 20% of the energy is wasted as heat, compared to more than 90% lost in a flame. That efficiency matters. Delicate organisms drifting in the water could never withstand fire in their tissues. They need light that shines softly without burning. Nature found a way. At the heart of this glow is a simple but elegant chemical dance. The main actor is a molecule called luciferin. The name comes from Latin lucifer, meaning light bearer. On its own, luciferin is stable and invisible. But when it reacts with oxygen, guided by a special enzyme called luciferase, it releases energy as a flash of visible light. Different organisms use slightly different forms of luciferin, which is why the shade of the glow varies. Bluish in the ocean, greenish in some insects, even reddish in a few rare cases. Think of luciferase as the key that unlocks luciferin's potential. Without the enzyme, the reaction is slow, faint, almost imperceptible. With it, the light can flare quickly, brilliant enough to ripple through waves or pulse across the body of a squid. And just as there are many species of glowing creatures, there are many variations on this chemical theme. Bacteria, for instance, use their own luciferins, often in colonies so dense they make entire patches of seawater shimmer like lanterns. In contrast, dinoflagellates, the tiny plankton that cause glowing bays to sparkle, carry a different type of luciferin altogether, one evolved in single cells that drift with the tides. Each lineage over millions of years found its own recipe for conjuring light. Why blue? If you've ever seen bioluminescence in person, you may have noticed the glow tends toward shades of blue-green. That isn't an accident. Water absorbs red, orange, and yellow wavelengths quickly. Blue and green travel farthest, cutting through the dark like beams designed for the ocean. Fish and invertebrates that live in the depths often have eyes especially sensitive to these colours. The chemistry and the physics meet in perfect harmony, a signal that can be seen where no sunlight penetrates. For centuries, people saw this light but did not understand it. Sailors wrote of fiery seas or phosphorescent waters. In medieval times, glowing fish or wood washed ashore were often seen as omens. It wasn't until the age of scientific experimentation that curiosity began to replace superstition. One of the earliest recorded investigations came from Robert Boyle in the 1660s, the same Boyle remembered for Boyle's law of gases. He noted that pieces of rotten wood and certain fish could glow without heat. Unlike a coal or a candle, their light did not burn. Boyle's experiments were simple. He observed, he compared, he reasoned, but they revealed something radical. Life could generate light without fire. 2 centuries later, in the 1870s, another leap in understanding came with one of the most ambitious scientific expeditions of the age, the voyage of HMS Challenger. This British naval ship was refitted for science, carrying naturalists and chemists across the world's oceans from 1872 to 1876. They dredged the seafloor, lowered nets into the abyss, and brought up creatures never before seen by human eyes. Among their observations was the widespread presence of light in the deep, squid with glowing organs, shrimp that could squirt luminous clouds, fish with lanterns dangling from their heads. For the first time, the glow of the ocean was not a sailor's tale, but a catalogued fact of biology. The Challenger expedition gave rise to the field of deep-sea biology. In their reports, they described how entire regions of the ocean seemed alive with light, a realm where illumination was not borrowed from the sun, but generated from within. These early accounts opened the way for later researchers to study the exact chemical nature of the glow. By the early 20th century, scientists like Raphael Dubois in France managed to isolate luciferin and luciferase, confirming the enzymatic dance at the heart of bioluminescence. There is a quiet beauty in how this history unfolds. From Boyle's dim observations of glowing fish, to Challenger's grand voyage, to modern labs sequencing the genes of glowing bacteria, each step has peeled back another layer of mystery, and yet even now, bioluminescence keeps secrets. We still do not fully understand why some lineages evolved light, while others did not, or how so many unrelated organisms stumbled upon such similar solutions. Evolution, it seems, loves light. When you think about it, bioluminescence blurs the line between the mechanical and the magical. In a lab, it can be written in equations, substrates, enzymes, photons. In the sea, it appears as rippling sparks in your wake, or as curtains of blue flashing beneath the waves. Science tells us how, but the feeling of it belongs to something deeper. Picture a scientist hunched over a microscope, watching faint sparks in a dish, jotting notes on a dimly lit desk. Then imagine stepping away from the lab, standing on the deck of a small boat at night and seeing the same glow spread across an entire bay, vast and alive. From the tiniest cell to the broad sweep of the ocean, the same reaction ties them together. And this is where we leave the lab bench behind. We close the notebook, turn down the lamp, and let the horizon take over. Ahead lies the living ocean itself, where single cells drift like stars, and deep-sea hunters wield their lanterns in endless night. The science of living light is only the doorway. Beyond it lies the theatre of creatures themselves, the actors who carry this ancient brilliance in their bodies. If you have ever seen the sea glowing under your fingertips, you have probably met the tiniest of performers, the dinoflagellates. They are single-celled plankton, microscopic drifters carried by tides and currents, yet capable of transforming whole shorelines into living galaxies. To the eye, they are invisible in daylight, just a part of the plankton soup that fuels marine life. But by night, when disturbed, They reveal themselves in flashes of radiant blue. Dinoflagellates are not plants, though some carry chlorophyll and harvest sunlight like algae. They are not animals either, though they swim weakly, using a pair of whip-like tails. They belong to their own branch of life, a group of protists, and they have thrived in the oceans for hundreds of millions of years. The mechanism of their light is elegantly simple. Each cell contains tiny sacs called scintillons that house luciferin and luciferase. When the cell membrane is mechanically disturbed by the stroke of a paddle, the rush of a wave, or even a darting fish, it triggers a rapid change in acidity inside the scintillon. That sudden shift activates the reaction, producing a brief flash of blue light that lasts just a fraction of a second. Imagine billions of these cells firing in chorus. The surface of the sea becomes a canvas of sparks. This glow is not constant. Dinoflagellates live by the rhythm of day and night. During daylight, they suppress their bioluminescence. Scientists have found that the number of scintillons inside each cell increases at dusk and peaks in the night, only to decline again by morning. It's as if they are programmed with their own circadian clock, tuned to darkness. The timing is practical. Glowing in the sunlight would be invisible and wasteful. In the deep of night, however, their light becomes unmistakable. Why glow at all? For a creature barely 1/10 of a millimetre across, it seems extravagant. The prevailing explanation is defence. When a fish lunges through a swarm of dinoflagellates, the water suddenly bursts into light, startling the predator. In some cases, the glow may serve as a burglar alarm, drawing the attention of even larger hunters to the small fish feeding on the plankton. To glow is to shout, "Someone is attacking me." For such fragile beings, light is both shield and signal. The visual effects are unforgettable. In some bays, kayakers leave glowing wakes that curl and vanish like liquid starlight. Swimmers see halos of blue explode around their arms and legs. Even a hand scooping through the shallows can spark showers of light, each drop glowing briefly before fading into darkness again. Along beaches, breaking waves look like ribbons of turquoise fire rolling to the sand. On the quietest nights, it can feel as though the Milky Way has poured itself into the sea. Different regions of the world have their own names for this wonder. In Australia, it is often called sea sparkle. In 2016, the beaches of Tasmania and Sydney lit up in extraordinary blue tides caused by the species Noctiluca scintillans. Photographs from those nights show entire coastlines glowing like neon strips, surfers surrounded by bright halos. The sight was breathtaking, though not entirely harmless. Blooms of Noctiluca are not toxic in themselves, but they can be associated with other imbalances in marine ecosystems. That raises an important distinction. Not all glowing swarms are benign. Some dinoflagellates also produce toxins that cause red tides, dangerous blooms that can kill fish, contaminate shellfish, and cause respiratory irritation in humans. These events often discolour the water a reddish-brown in daylight and glow eerily at night. In contrast, many bioluminescent blooms are harmless, serving only as a visual spectacle. Understanding the species involved is crucial. The same shimmering glow that delights beachgoers can, in other contexts, signal ecological trouble. Scientists are still learning what controls the intensity of the glow. Recent genetic and physiological studies suggest that the strength of bioluminescence is linked to the stress levels inside the cell. A healthy dinoflagellate might flash brightly, while one starved of nutrients or exposed to pollutants may glow weakly. Some researchers propose that light output could serve as a kind of biological indicator, an early warning system for ocean health. By measuring the faint blue sparks of plankton, we may glimpse changes in the chemistry of entire seas. One of the most remarkable habitats for dinoflagellate bioluminescence is the bioluminescent bays of the Caribbean, especially Mosquito Bay in Vieques, Puerto Rico. Here, billions of dinoflagellates called Pyridinium bahamense gather in the shelter of mangroves. The bay's geography, a shallow lagoon with limited circulation, keeps the cells concentrated. Visitors who kayak into these waters on moonless nights describe paddles trailing fire, fish darting like comets, and hands glowing with every touch. In 2008, Mosquito Bay was recognized by Guinness World Records as the brightest bioluminescent bay on Earth. But even outside of these rare lagoons, dinoflagellates can appear almost anywhere. Sailors throughout history have reported fiery seas as their ships carved glowing paths across the oceans. Charles Darwin wrote of them during the voyage of the Beagle. Mariners often considered the glow either a blessing or an omen, unaware that the spectacle came from countless invisible cells reacting in unison. There is something humbling in this knowledge. The tiniest life forms, too small to see individually, can combine to create phenomena vast enough to awe entire cities. Dinoflagellates remind us that scale does not determine wonder. A billion pinpricks of light, fleeting and fragile, can turn the sea into a stage of living stars. And so, when you see the surf glowing or your footsteps lighting up the sand, know that you are witnessing a conversation among creatures older than humanity itself. They have no voices, no eyes, no awareness of your presence. Yet their reaction to your touch, the shimmer they leave in your path, links your movements to theirs in a brief, dazzling moment. From the perspective of science, the explanation is clear. A chemical reaction triggered by stress in a single cell. From the perspective of the heart, it feels like magic, the ocean answering your gestures with light, and that is where we will leave the shore. From here, we move out into deeper waters where larger creatures carry their own lanterns, where fish and squid turn the darkness of the deep into a silent theatre of living light. If the glow of dinoflagellates along a shoreline feels like starlight spilled across the waves, then the deep sea is an entire universe of living constellations. Beyond the reach of sunlight, below 200 meters, where the ocean becomes a twilight zone, light is scarce, but life has not accepted darkness as its fate. Instead, countless creatures have woven light into their very being: fish, squid, shrimp, jellyfish, even worms. The deep ocean is not black, but alive with glimmers, flashes, and silent lanterns. Marine biologists estimate that more than 80% of deep-sea animals are bioluminescent. This means that in the largest habitat on Earth, light is the rule, not the exception. But unlike the steady glow of the sun, this is a living light, used strategically. Each flicker serves a purpose: survival in the dark. At first glance, camouflage might seem impossible in the open ocean. There are no rocks to hide behind, no trees, no walls, only endless water. Yet fish have learned to blend in, not by hiding, but by glowing. The lanternfish, one of the most abundant creatures in the sea, has bellies lined with tiny photophores, specialized light-producing organs. From below, the faint sunlight filtering down makes their bodies cast a silhouette. Predators looking upward can spot them easily. But lanternfish solve this with a trick called counter-illumination. They light up their undersides with a soft blue glow, carefully matched to the faint glow of the water above. The effect erases their shadows. To a hunter peering up from below, the lanternfish vanishes, perfectly blended into the background. Many squid and shrimp use the same strategy. Some can even adjust the brightness of their photophores in real time, dimming or brightening, to stay invisible as conditions change. In the deep, light is not only a beacon, but also a cloak. Other creatures turn their glow into a weapon. The most iconic is the anglerfish. With its grotesque mouth and sharp teeth, it would be fearsome enough, but it also dangles a luminous lure from its forehead, a modified dorsal spine tipped with glowing bacteria. In the endless night of the abyss, curious prey are drawn to the light, mistaking it for a smaller organism. When they come close, the anglerfish snaps them up in an instant. Dragonfish, long eel-like predators armed with rows of teeth so transparent they are nearly invisible, possess light organs under their eyes that project beams into the water, much like headlights on a car. With this stealthy torch, they scan the darkness for unsuspecting prey. Some species even produce red bioluminescence, which is particularly clever. Most deep-sea creatures cannot see red light, so the dragonfish can shine its searchlight without being detected. To the dragonfish, the world glows. To its prey, the hunter is invisible. Other hunters use light in subtler ways. The cookie-cutter shark, a small predator with a big reputation, uses photophores on its belly to disguise itself against the faint light above, while keeping a small patch unlit. From below, this patch looks like the silhouette of a smaller fish. When larger predators move in for what they think is easy prey, the cookie-cutter ambushes them, biting out a circular plug of flesh before swimming away. Light becomes a decoy in a game of deception. Not all bioluminescence is about hiding or hunting. Some of it is about love. Every summer in tropical waters, fireworms rise in glowing swarms to reproduce. Females release bioluminescent chemicals as they swim in circles near the surface, their bodies glowing greenish blue. Males, sensing the light, rush toward it, releasing their sperm into the water. To see such a swarm is to witness the sea sparkle with hundreds of tiny, glowing signals, an entire mating ritual written in light. Other animals use more personal courtship displays. Some species of squid flash patterns along their bodies, like illuminated tattoos, signalling readiness to mate. In a realm where sound and colour are muted, light serves as the most eloquent communication. It is difficult to overstate just how widespread bioluminescence is in the deep ocean. From microscopic plankton to 6-foot-long predators, from drifting jellyfish to tiny worms, the majority of creatures here shine in some way. Some emit steady glows, others pulse rhythmically or explode in sudden bursts, creating underwater fireworks. Jellyfish can trail glowing curtains behind them, a kind of diversionary trap to confuse attackers. Shrimp can squirt glowing clouds into the water, much like squid ink, giving them time to escape. If we could turn off all human lights, sink a submarine into the midwater depths and simply watch, we would see a slow-motion thunderstorm of sparks and flashes in every direction, a silent theatre, vast beyond imagining. The glow of the ocean has not only fascinated scientists and poets, it has influenced history. During World War II, submariners learned to fear bioluminescence. A vessel slipping silently through the Pacific could sometimes trigger glowing patches of plankton in its wake, leaving behind a bright trail visible from aircraft above. Stealth missions were betrayed by light that could not be controlled. Reports tell of captains altering their routes, desperately avoiding waters known to glow. In the balance between survival and discovery, even the smallest plankton played a role. Imagine yourself now inside a deep-sea submersible, lights turned low, windows facing out into the abyss. The world outside is black, but not empty. Slowly, tiny sparks drift by, jellyfish pulsing like lanterns, shrimp leaving trails of faint light, fish with glowing spots shimmering as they swim past. Occasionally, a burst of brightness erupts, a startled squid discharging a cloud of glowing fluid. The scene feels otherworldly, like drifting through a galaxy where each star is alive, each light a signal of hunger, fear, or desire. Time slows in such a place, the silence of the water, the slow pulse of the glow. It is easy to forget you are still on Earth. The deep sea is not merely a curiosity. It is a world built on light, fragile and yet unrelenting, where survival has been written into chemistry and colour. From lanternfish erasing their shadows, to dragonfish scanning with invisible beams, to fireworms spiralling in glowing dances, each creature carries a role in this vast and silent performance. And as we drift away from the abyss, we rise toward waters where the light is concentrated, where entire bays glow with the gathered power of billions of tiny cells. If the deep is a theatre, then these bays are amphitheatres, grand stages where the audience can join the show simply by dipping a hand into the water. The ocean glows in many places, but a few corners of the world have gathered so much light that they feel almost mythical. These are the bioluminescent bays, lagoons, and beaches where the conditions align perfectly, where billions of tiny plankton collect in sheltered waters, and where a quiet night can turn into something unforgettable. Perhaps the most famous lies in the Caribbean, on the small island of Vieques in Puerto Rico. It is called Mosquito Bay, though its name hardly suggests its wonder. Here, the concentration of glowing dinoflagellates is higher than anywhere else on Earth. In 2008, Guinness World Records declared it the brightest bioluminescent bay in the world. On moonless nights, every paddle stroke through its calm waters leaves behind a streak of electric blue. Fish darting below look like shooting stars, their movements traced in light. Tourists who dip their hands in the bay often gasp softly, watching glowing droplets fall from their fingers like liquid sparks. The glow is so intense that even the gentle wake of a kayak can look like fire carved into the sea. Not far away, still on Puerto Rico's coast, lies Laguna Grande in Fajardo. The lagoon is reached through a narrow mangrove channel, branches curling overhead like the frame of a dark cathedral. At the end, the waters widen into a basin where dinoflagellates gather in great numbers. Guides bring small boats here at night, and as the paddles move, the surface blooms with streaks of blue-green fire. The mangroves are essential. They shelter the lagoon from currents, keeping the organisms inside, while their roots provide nutrients that feed the plankton. Further west on the island, La Parguera offers yet another glowing bay. Unlike Mosquito Bay, which is heavily protected, La Parguera allows limited swimming. Visitors slip quietly into the warm Caribbean water, moving their arms through liquid galaxies. Each motion is answered with light. Even the smallest gestures, a kick, a hand lifted, a body turning, scatter blue halos that spread, shimmer, and fade. For many, it is their first intimate encounter with a glowing sea, one that lingers in memory long after the night ends. In nearby Sainte Croix, the US Virgin Islands hold another treasure, Salt River Bay. Here, not only dinoflagellates, but also glowing jellyfish and ctenophores add their light to the lagoon. On the right nights, the bay feels like a cosmic aquarium, with multiple forms of bioluminescence flickering in unison. Scientists believe the sheltering geography and nutrient inflows create a perfect nursery for these organisms, a reminder of how delicate and precise the recipe for living light can be. The Caribbean is not the only stage for this wonder. In Jamaica, the Luminous Lagoon near Falmouth glows so brightly that it was once used by boat captains to navigate at night. Today, small craft take visitors out into the lagoon, where the water flashes with each motion of the oars. Swimmers descend into it, their bodies traced with faint glowing outlines. Local guides sometimes tell stories of spirits in the water, but the true magic is even stranger: 1 billion invisible plankton answering every touch. Far across the world, the Maldives are famous for beaches that seem to glow beneath the stars. Along certain stretches of sand, the breaking waves light up as though fireflies were trapped in the foam. At night, couples walking along the shoreline see each step flash with faint blue halos. The glow comes and goes, depending on blooms of plankton, so it cannot be guaranteed. But when it appears, the entire beach seems enchanted, the sea glowing softly against the vast dark of the Indian Ocean. Japan, too, has its own spectacle. In Toyama Bay, every spring, millions of firefly squid rise from the depths to spawn. Their bodies are lined with photophores that emit a bright blue glow. As they gather near the shore, the water shimmers with their combined light. For fishermen and visitors, the event is both practical and breathtaking. The squid are harvested, but their luminous displays turn the bay into a theatre of living lanterns. Unlike the passive glow of plankton, this is active bioluminescence, a species signalling and communicating, filling the shallows with pulses of blue. These spectacles depend on fragile conditions. Sheltered lagoons are key, places where tides cannot sweep the organisms out to sea. Mangroves often play a role, their tangled roots protecting the waters and feeding them with nutrients from decaying leaves. Warm, stable temperatures help sustain plankton blooms, while calm weather keeps them close to the surface where they can be seen. Too much turbulence, too much pollution, and the light disappears. For the human eye, the best view comes on dark, moonless nights. Even a sliver of moonlight can drown out the glow, just as city lights drown out the stars. Visitors who come during storms or heavy winds may leave disappointed, the water stirred too violently for the plankton to shine. But on still nights, when the air is quiet and the sea rests, the glow emerges. It is a phenomenon not only of biology, but of timing. To travel to one of these bays is to step into a scene that feels both intimate and infinite. Picture yourself in a small kayak, gliding silently through Caribbean blackness. The air is thick with the smell of salt and mangrove leaves. Each drop from your paddle falls as a spark, scattering blue light across the water. Below you, fish dart, their bodies flashing like meteors. Around you, darkness is total, except for the glow that blooms with every motion. The effect is dreamlike, a night sky mirrored in liquid form, stars not above, but below. Some visitors say the experience feels like drifting inside a universe turned upside down. Others describe it as childlike joy, the wonder of realizing that your own hands, your own movements can stir the ocean into light. There is no switch to turn on, no device, no machine, only the ancient chemistry of single cells awakened by your presence, shining briefly before fading back into the dark. From Puerto Rico to Japan, from Jamaica to the Maldives, these glowing seas remind us of the ocean's quiet generosity. They are fragile, fleeting, easily disrupted by human activity or climate change. Yet for now, they continue to burn gently in their hidden corners, ready to astonish anyone willing to venture into the night. The glow of the sea feels eternal when you are there in the moment. It seems as though the ocean has always carried this secret fire, as if it could never be lost. But bioluminescence is fragile. It depends on delicate balances in water chemistry, on the shelter of mangroves, on darkness itself. Human actions, even unintentional, can disturb these conditions, dimming a phenomenon that feels as old as the stars. Along many coasts, development has crept closer and closer to the shore. Hotels, roads and houses bring runoff from the land, fertilizers, sewage and pollutants that alter the nutrient levels of lagoons. Too much nitrogen can trigger harmful algal blooms that overwhelm or outcompete the glowing species. Boat traffic adds to the strain. Propellers churn the waters, engines leak oil, and noise disturbs ecosystems. Even light pollution from nearby towns or beach resorts can drown out the glow. For organisms that shine best in pure darkness, a single floodlight can erase the magic. Tourism, too, leaves its mark. In Puerto Rico's bioluminescent bays, the number of visitors has surged in recent decades. Kayaks crowd the lagoons at night, and eager swimmers stir the water, sometimes coating themselves in glowing halos. It is enchanting, but every splash stresses the plankton. Sunscreen and insect repellent wash off bodies into the water, chemicals that can poison the fragile cells. Some bays have seen noticeable declines in brightness, forcing local authorities to restrict activities. In Mosquito Bay, swimming is now forbidden and only non-motorized boats are allowed. The regulations may feel strict, but without them, the brightest bay in the world could fade. Beyond direct human impact lies the broader shadow of climate change. Rising ocean temperatures shift the balance of plankton populations. Some species bloom earlier in the season, others retreat. Warmer water holds less oxygen, adding another layer of stress. Acidification from increased carbon dioxide alters the chemistry of the seas, threatening not only coral reefs, but also microscopic organisms like dinoflagellates. Scientists monitoring bioluminescent bays have reported fluctuations in brightness from year to year, some of which may be linked to global climate patterns. The cycles of bloom and glow that once felt steady are becoming less predictable. Storms are another factor. As hurricanes grow stronger with warming seas, they churn lagoons and disrupt the calm waters that plankton need. After major storms, some bays lose their glow for weeks or months as the delicate balance of salinity and nutrients is reset. In 2017, Hurricane Maria struck Puerto Rico with devastating force. For a time, Mosquito Bay seemed dark. Locals feared the glow was gone forever. Yet, slowly, the organisms returned. The resilience was heartening, but it was also a reminder: the light is not invincible. Conservation efforts have become essential. In Puerto Rico, strict limits now regulate access to the bioluminescent bays. Boats must use designated routes, no motors are allowed inside, and only trained guides may bring visitors. Education is part of the effort. Tourists learn why they cannot swim, why they must avoid chemicals, why the glow is not guaranteed. These measures help protect the fragile ecosystem, giving the plankton a chance to thrive in peace. In some bays, the brightness has even improved after years of careful protection. It shows that with respect and restraint, the glow can endure. Science is also finding ways to bring bioluminescence into new realms, sometimes as a tool for conservation, sometimes as inspiration for design. Researchers have harnessed bioluminescent proteins as biosensors, using them to detect pollutants, measure cellular activity, or track genetic expression. In medicine, the glow of luciferase is used in research to illuminate tumours or follow infections inside living organisms, offering a non-invasive way to see what would otherwise be hidden. Engineers and artists have experimented with glowing plants and bacterial art, imagining a future where city streets are lit not by electricity, but by bioluminescent trees or glowing walls. These ideas remain experimental, but they point to a fascinating possibility: learning from the ocean's light to create gentler, more sustainable forms of our own. Yet there is a fine line here. Artificial bioluminescence may inspire wonder, but it is not the same as standing in a dark lagoon, the silence broken only by water lapping against a boat, the glow blooming naturally with each motion. The laboratory glow is useful, even beautiful, but the living glow of the sea carries something irreplaceable. It is older than our species, unshaped by our hands, a gift of evolution that arrived without our asking. To witness it is to be reminded of how easily wonders can slip away. We often think of light as something permanent. Flip a switch and it is there. But in the sea, light depends on fragile creatures responding to delicate triggers. Too much noise, too much heat, too many chemicals, and the glow dims. Imagine again the paddle dipping into Mosquito Bay, scattering blue sparks. Imagine the quiet hush of a Maldivian beach, each wave curling in neon. Imagine the firefly squid rising in Japan, filling the shallows with their luminous bodies. Each of these spectacles exists only because nature's balance holds. Each can fade if that balance is broken. The light of the ocean is not just a spectacle, it is a fragile gift. To see it is to step into an ancient story still unfolding, written in the language of chemistry and carried by creatures smaller than a grain of sand. To protect it is to honour the mystery that we are lucky enough to witness, and to reflect on it gently is to realise how much of our world depends on things that glow quietly, unseen, until the darkness reveals them. And so we return to the shore where it all began. The night is quiet, the sea calm, and the glow lingers with every ripple. You've travelled through the science of this living light, the tiny plankton that spark at your fingertips, the hunters of the deep who wield lanterns and lures, the bays and lagoons that hold entire galaxies in their still waters. You've seen how fragile it all is, shaped by balance, threatened by change, yet still enduring, flickering, answering every movement with a gentle shimmer. When you think back on it, light has always been our guide. We gather around fires, we read by lamps, we navigate by stars. Bioluminescence is another thread in that long story, a light that needs no fuel, no wires, no hand to strike the flame. It is the ocean's own lantern, drifting endlessly in the dark. Now imagine again the water beneath your hand. You stir it gently and blue sparks bloom and fade. They appear for only a moment, then vanish into stillness, as though the sea has whispered a secret and then fallen silent. The glow is temporary, yet unforgettable. Let yourself rest in that thought, the quiet rhythm of waves, the endless horizon, the sparks of living light that come and go like fleeting dreams. You don't need to hold on to them, just drift with them, softly, slowly, into calm. Close your eyes, breathe with the tide, and let the sea carry you gently into sleep.